Good day, everyone. Today, I'll be talking about the works of Dr. Saitis et al. 2022, entitled Beachrock Formation Mechanism Using Multi-Proxy Experimental Data from Natural and Artificial Beach Rocks, Insights for a Potential Soft Engineering Method. Sandy beaches represents about almost one-third of the ice-free global coastline. They have a huge socioeconomic importance, including residency, recreation, tourism, industry, agriculture, aquaculture, fishing, and even energy production plants are located close to sandy beaches. However, beach erosion poses a threat to all of these relevant stakeholders, and particularly to the tourism industry. Recent studies by Vidukas et al. 2020 found out that almost 13.6 to 15.2% of the world's sandy beaches might face beach regression by the year 2050. And these numbers may even rise up to 35.7 to 49.5% by the year 2100. Furthermore, climate change may even accelerate the intensity of storms and global sea level rise, thus affecting coastal erosion even further. Traditionally, hard engineering structures such as seawall, groins, piers have been used to manage storm tides and protect the development within a coastal zone. However, these require long periods of engineering time and are very expensive and have a high impact on the natural coastal scenery, making them less appealing. On the other hand, soft engineering techniques use soft methods such as dredging, beach nourishment, and beach scraping to limit erosion and achieve shoreline stabilization. These methods are less intrusive to natural coastal processes compared to hard structures. Beach rocks are hard coastal deposits that consist of a wide variety of beach sediments identified at the shoreline through the precipitation of calcite and its magnesium polymorphs. Beach rocks are most commonly found on the Mediterranean, the Caribbean seas, the tropical and subtropical Atlantic coast of Brazil, Japan, Australia, as well as atolls in the Pacific and Indian Ocean. A particular characteristics of sandy beaches that host beach rock is that they are less impacted from erosional processes, and they even maintain their morphological and sedimentological characteristics. So they have a clear protective role in these coastal areas. Microbial-induced carbonate precipitation, MICPs, is an innovative, eco-friendly, and sustainable technique to create artificial beach rocks in the laboratory. MICP techniques are a promising method where bacteria essentially is used to precipitate calcium carbonate and modify soil characteristics, resulting in soil consolidation and stabilization. Using MICP, it is possible to imitate the formation of natural beach rocks as a countermeasure against soil erosion. The major metabolic process involved in MICP is urea hydrolysis, wherein urea, through the action of urease enzyme and with the help of carbonic anhydrase, is hydrolyzed and essentially induces the precipitation of calcium carbonate in the presence of soluble calcium 2+ in the environment. So for the objectives of this study, number one is to provide an insight into soft engineering solution for protecting vulnerable coastal zones from erosion. Number two is to study the beach rock sedimentation process by comparing the characteristics of natural beach rocks and the in vitro artificial beach rocks in terms of their mineralogical and geochemical properties. Now for the methodology, we have two case studies that are examined from different geological and geographical settings. Now, the first one is the Olcos site located in the Gulf of Current, as you can see right here. So the Olcos site is in the Gulf of Current, and as you can see, is the Gulf of Current, and it is connected by the Corinth Canal to the Saronic Gulf. On the north, you have central Greece. On the south, you have the Peloponnese. On the other hand, Sumida site is located in Okinawa Island and the Ryukyu Island of Japan, which is located on the south of the main island of Japan and is considered the youngest back arc rifting belt in the East China Sea. Now for the detailed procedure of bacterial cultivation, what happened here is that we get sediment sample from these two different sites. We isolate the bacteria using a special type of medium called the Zubel marine medium, and we use an artificial seawater to dilute that. In my experience, this is the most difficult part of the job because you have to measure each and every one of these salts just to make the artificial seawater. So we're going to use this medium and we're going to culture the bacteria to isolate a single bacterium. And then after producing a pure isolate of that bacterium, we're going to amplify the 16S rRNA gene region of the bacteria, and we're going to subject it to gene sequencing to have the identity of our pure cultures. Now, the end point right here is we'll have this test tubes of pure cultures of these bacteria, and we're going to inoculate some of them to this Erlenmeyer flask in an rotating shaker incubator. And the end product here would be these two bacterial solutions right here. And we're going to check the density of this bacterial solution using UVB spectrophotometer at wavelength of 600 nanometer. So for the syringe solidification setup and the artificial Beachrock experiment, I would like to now to tell you that we have 3 experimental setups. One is from Greece and the other 2 is from Japan. The only difference between the 2 samples from Japan is that they perform 2 different experiments with 2 different concentration of bacteria. The first one is the higher concentration. The second one is the lower concentration of bacteria. Now, in the artificial Beachrock experiment, these 3 experimental setup essentially looks like this, where you have your sediment sample that has the same granulometry from the site, and you mix it with the bacterial solution in this syringe setup right here. The sand is saturated with and cured with the bacterial solution, and as you can see here, we have the control valve to control the flow of the outlet solution. Again, we need to measure the pH and calcium 2+ concentration of this outlet solution, so we have the temporal gradient of these parameters because this indicate the bacterial metabolic processes that is happening. And for 14 days, during a specified fixed interval, we're gonna pour a cementation solution in the syringe solidification setup. We're gonna put them in this incubator right here. This is how they look like. And after 14 days, we're gonna cut them up. We're gonna extract the artificial Beachrock from them. We have the bottom, middle, and top portion, and we're gonna subject it to needle penetration test using this device right here. And we are also going to perform different mineralogical and geochemical analysis using petrographic microscope, SEM to EDX and XRD machines. Now for the results and discussion, the material isolated from Greece is Micrococcus yunonensis, which is a gram-positive coccus bacteria. And the case of Japan, we isolated Pararhodobacter sp, which is a gram-negative bacteria. Now, for the case of natural Beachrocks, in terms of their micromorphology based on SEM and microscopic examination, we found out that for the case of all these natural Beachrock, the sediment texture of the studied Beachrock is always connected with the recent sedimentary processes of each area, which supplies the material from the corresponding weathered bedrock. So for the case of the Olcos site, we have, in terms of its major component material, we have a variety of consolidated lithoclasts with minerals and mineral grains with differences of material density and hardness, which mostly came from heterotrophic erosion and slaking of minerals with a variety of sizes in the consolidated sediment, from very fine sand to pebbles and even gravels. For the case of Sumoide Beachrock, we have a sediment that is mostly derived from the local coral reef of the Okinawa island. And thus, its texture is more of uniformly sandy with a lot of fossilized skeleton parts of foraminifera and coral parts. In terms of their cement composition, for the case of Greece, we have the Iolcos Beachrock has a very typical high magnesium calcite in micritic and sporitic crystal forms. The high magnesium calcite micritic cement indicates a marine provenance, but the matrix formation in the pores of the sediment also indicates the mixing of sea and fresh water. While for the case of Sumuide Beachrock in Japan, it's a different case because it's characterized by a well-developed coating of micritic HMC with an abundance of sporitic calcite crystal and aragonite of up to 20 micrometer in size. The calcareous sediment composition of Sumuide site favors the formation of calcite and coarse needle of aragonite, which occasionally was recrystallized and formed smaller sporitic crystals. The coexistence of these different types of cement indicates a low intertidal or upper subtidal zone precipitation, as it's mostly affected by the marine environment. So these are the images of polarized microscopy and also SEM images. As you can see here, for the case of the Iolcos, Greece, we have a micritic HMC cement coating of calcite grain and also of quartz grain. And for the case of Sumuide, Japan, we have a very well crystallized calcite and aragonite needles coating of calcite of these calcite grains, and even these microfossils right here. As you can see, inside these microfossils, we have sporitic and aragonitic needles inside of it forming, and also in the vents of these microfossils right here. Now moving on to the case of the artificial beach rocks, it made sense that the sediment grains are similar in shape and composition with the natural beach rocks of the corresponding beaches, because we made sure that in the experimental setup, they have the same granulometry. The cement composition of the artificial beach rock from Greece is characterized by micritic and sporitic crystals of calcite in various sizes from 10 micrometer to 100 micrometer. Additionally, a discontinuous fan-shaped grain coating was observed along with microcrystalline calcite serving as pore filling with thick crystals of aragonite. For the case of the artificial beach rock from Japan, the two samples consisted of very similar grain shape and composition to the local beach rock. Their cement was made of particularly well-developed aragonite crystals with lengths of around 10 micrometer to 20 micrometer. For the polarized microscopy images and SEM images, we can see here we have microcrystalline calcite cement. Here we have a micritic sporitic calcite cement forming a very defined fan-shaped grain coating. Again, here we have well-developed calcite cement and also a fan-shaped grain coating right here. For the case of the artificial beach rock in Japan, we have a well-developed crystals of aragonite coating the sediment right here. We have crystals of aragonite and matrix cement working as a pore filling in this foraminiferal shell. Again, here, the two sediments are well joined by the aragonite crystals. And again, these two grains right here are, as you can see, the aragonite needles are well developed. Now for the pH and calcium 2 plus concentration of the outlet solution, basically what we need to remember here is that the low pH concentration is equal to high urease activity, and the low calcium 2 plus concentration is equal to increase in precipitation of calcium carbonate. So we can see here we have high bacterial activity until the 5th day and the 8th day, and during the last 3 days of the experiment, and also calcium 2 plus concentration follows that trend. For the case of Sumuide, Japan, of course, the one with a higher concentration of bacteria has a higher response to, has a lower calcium 2 plus concentration and has a higher pH activity. Lastly, we have the results for the USC needle penetration test. The general trend for all of the sample is that the upper portion of the artificial beach rock is generally has a higher USC penetration rating compared to the bottom portion of the artificial beach rock. This is due to the fact that the bottom resident bacteria were partially able to participate in the entire urease activity process, and at the same time, the higher concentration of organic material and waste product could possibly induce, and bacterial mortality could induce some local changes in the environment of the bacterial living condition. Also, as we can see here, the artificial beach rock from Greece has a more consolidated sample, although this zero value right here is due to the fact that the sample actually has consolidated a 2 millimeter size of sediment. That's why your needle penetration test can be performed. Furthermore, for the case of the artificial beach rocks of Japan, we can see that the artificial beach rock that was created using a higher concentration of bacteria usually perform better in the USC needle penetration test. In conclusion, artificial beach rock could lead to a new era of sustainable soft engineering construction where it can imitate natural beach rock characteristics as breakwater. By creating artificial beach rocks in vulnerable sandy beaches affected by erosion, we can achieve eco-friendly and sustainable coastal management plan that saves energy, reduce our CO2 emission, reduce the requirement for building materials, and possibly imitate the natural occurrences of beach rocks, improving positive impact on marine biodiversity.